So how this K equals to radical of I divided by M occur? Tumetoa wapi hii formula? Let us recall for the moment of inertia. As we know that from our figure here, the moment of inertia here must be equals to mr square. If it is equal to mr square, now for the sine word here, the r is equal to k. If it is equal to k, now we could say that moment of inertia is equal to mk square. If it is equal to mk square, but as we wanted to make k as the subject which represented the radius of gyration, now we could say that k must be equals to radical of I divided by r, as we tried to demonstrate. Kwa hiyo ukitokea kwenye moment of inertia ni sasa na mk square, uta divide by m, na baada ya kudivide by m uta apply radical throughout. Mwisho wa siku utaipata hii formula ya ambayo ina represent radius of gyration of a rotating liquid body. So this should be the question number 63 for our fourth topic. So if a mass of the body is assumed to be concentrated at a point with a distance k from the axis of rotation, the moment of inertia by definition is given by this one. So if we assume that the moment of inertia is concentrated, now how can we define the moment of inertia? How can we define the moment of inertia if we assume the mass is concentrated? So from this one, from I, as I told you that from I equals to mk square, but we know that this m represented the concentration of the mass, and also I represented the moment of inertia, while k represented the radius of gyration for a rigid body. So we are supposed to introduce the summation if we have more elemental disk. Tunapokuwa sasa tuna distance nyingi sana, tuna radius nyingi sana kwenye ile thin word. Now we should introduce the summation, and we could say that therefore I is equal to the summation of mri square. Lakini huyu I anakuambia kasa kwamba tunapokuwa na radius nyingi, na tumeshaona kasa kwamba huyu I ataanzia ni sawasawa na moja up to the nth terms if we have more radius. So if we factor out this m, because m it is constant and the I and the ri it is vary, now we can say that the moment of inertia must be equals to m times the summation from I to n, then we times it by ri square, and this could be the equation number 64 for our fourth topic. Now this is demonstrated from mk square, where k could be the radius, lakini wale radius wanaweza wakavari. Tunaweza tukawa kwenye ile scene au kwenye ile solid disk, tunao wengi sana. Tukiwa na wengi sana lazima tutaintroduce summation. So after this one, my dear student, if the body of mass m is made of any particles each of mass m, then the largest the capital M must be equals to mn, and we could say that therefore the least m must be equal to capital M divided by n. Therefore we should say that from our equation number 64, as we try to see from this equation, and also from the equation number 63 here. Now we say that k can be expressed as equals to this one. If we consider two equations, the equation number 63 and also the equation number 64, now we should obtain that the k which represent the radius of gyration for a rotating liquid body must be equals to the summation. It means must be equals to the summation of ri square, then we add it by n. But where this n ni number of that radius, it means this is the number of radius, the n stems, idadi ya wale radius ambao tutakuwa nao kwenye ile solid disk au kwenye sine word disk. So we know that if we want to define the summation of Ri could be equals to Ri square, then we add it by R2 square, we add it by R3 square, then we add it by dash addition of R square n stem. And this will be our equation number 65 for our 4C topic. Now we could say that therefore sometime instead of writing the radius of gyration equals to the square of moment of inertia divided by the mass of the disk, we should represent sometime the moment of inertia equals by the radical of the summation of Ri divided by n. But the summation of Ri must be equals to R1 square, we add by R2 square, we add by R3 square, we add by dash and 3 to the n stems of R square, and then we divide it by n. So this is our equation number 65 for our 4C topic. And we could say that K should represent the root mean square distance and is some kind of the average. So this K must represent the root mean square. Kwa ile K ita represent ni root mean square, au sometime tunaita ni radius of gyration for a rotating rigged body. Kwa itakuwa na majina mawili. Either you can call as the root mean square, or you can call as the radius of gyration for a rigged body. So this K, as I told you, my dear student, will be as the radius of gyration for a rotating rigged body, or could be equals to root mean square. And sometimes we say that this K must be either the average effective distance of the particles from the axis of rotation. Kwa hiyo utaulizwa pale, je, ile K ina represent kitu gani? Utamwambia tunaweza tukaiita hii ni radius of gyration, au ni root mean square, au ni average distance of the particle from the axis of rotation. So therefore the radius of gyration of a body about a particular here axis of rotation is equal to the root mean square distance of its particles. So the radius of gyration of about the axis of rotation must be equals to the root mean square. Kwa hiyo radius of gyration ya ile rotation of the rigged bodies atakuwa ni sawa na ile square distance ya zile particles from the axis of the rotation. So there are so many questions here you'll be asked, my dear student. One of the questions you'll be asked to define the first task is that can you define the meaning of the radius of gyration? Give the meaning or the definition of the radius of gyration. But the second definition, the second question or the second task that you'll be asked here is that can you prove that the radius of gyration is equals to the radical of I divided by m? And also you'll be asked that please show the radius of gyration of the rotation of a rigged body is equals to the root mean square. Only 3 questions that you'll be asked for this session. So by saying that, my dear student, this is the end of our session here. Now I would like to invite you again for another session. I wish you all the best. Have a nice moment.